A planet that has been photographed, sketched, and stared at through telescopes for more than 400 years, ever since Galileo first pointed a crude spyglass at the sky and saw something strange attached to its sides, something he couldn't quite explain. 4 centuries of observation, dozens of spacecraft flybys, a 13-year resident orbiter that mapped its rings down to the width of a highway. And yet, in the spring of 2026, 2 of humanity's most powerful space telescopes pointed at that same planet at the same time in different colors of light and produced something nobody had ever seen before. A view so layered, so detailed, that scientists are calling it the most comprehensive picture of Saturn ever assembled. This isn't hype. This isn't a clickbait exaggeration dressed up as science news. This is NASA, on the record, saying that the James Webb Space Telescope and the Hubble Space Telescope teamed up, pointed their very different eyes at the ringed planet, and revealed a world that looks almost like 2 completely different planets, depending on which wavelength of light you're using to look at it. So today, we're going to break down exactly what these telescopes saw, why it matters, and what it tells us about a planet that, even after 400 years, still keeps secrets. Let's get into it. Before we get to the images themselves, it's worth asking a simple question. Why does a planet we've already sent a dedicated orbiter to, why does a planet millions of amateur astronomers have photographed from their backyards, still deserve this kind of attention from the 2 flagship observatories of modern astronomy? Well, the answer has everything to do with time. Saturn takes roughly 29.5 Earth years to complete 1 trip around the Sun. That means a single Saturnian year is longer than most people's entire working careers. And because Saturn's axis is tilted, just like Earth's, it experiences seasons, real seasons, with a northern summer and a northern winter, a southern spring, and a southern autumn. Except each one of those seasons lasts more than 7 years. That long time scale is the whole point. If you only look at Saturn once, you get a snapshot. If you look at it again and again, year after year, decade after decade, you start to see something else entirely. You start to see a living, breathing atmosphere that changes with the seasons the same way Earth's does, just on a scale so vast it's almost impossible to comprehend. Storms that last for years instead of days, cloud bands that shift color as sunlight angles change, a hexagonal jet. Stream at the North Pole that has held its shape since Voyager first noticed it back in 1981. That's the scientific mission behind these images. It isn't just about capturing a pretty picture for a press release. It's about extending an unbroken chain of observation that started decades ago and will keep going for decades more, so that when future scientists ask what changed on Saturn between 2024 and 2054, there's actual data to answer that question, not guesswork. Here's where it gets genuinely fascinating and where a lot of casual space fans get confused. The James Webb Space Telescope and the Hubble Space Telescope are not simply one is newer and better than the other. They see completely different things because they are built to detect completely different kinds of light. Hubble, which has been flying since 1990, is primarily a visible light and ultraviolet telescope. It sees the universe roughly the way our own eyes would see it, if our eyes were sensitive enough to gather that much light over that much time. When Hubble looks at Saturn, it's essentially photographing sunlight bouncing directly off the tops of the clouds, the same way a camera on Earth photographs sunlight bouncing off a mountain range or an ocean. Webb, which launched on Christmas Day 2021 and has been operating since 2022, is fundamentally an infrared telescope. Infrared light sits just beyond what human eyes can detect, and it behaves very differently when it interacts with the planet's atmosphere. Instead of just bouncing off the very top layer of clouds, certain infrared wavelengths can penetrate deeper, revealing structures, chemicals, and temperature variations that are completely invisible in ordinary visible light. Scientists have a wonderful way of describing what happens when you combine these 2 views. They call it slicing through GH, the atmosphere, like peeling back the layers of an onion. Hubble shows you the surface, Webb shows you what's underneath. Put them together, and instead of a flat 2-dimensional snapshot, you get something closer to a 3-dimensional model of how Saturn's atmosphere actually works from Thieger. Deep, warm clouds far below, all the way up to the thin, cold haze at the very edge of space. That's exactly what happened here. NASA released a pair of images, one from each telescope, and even though it's the same planet, it barely looks like it. Now her is an important detail that a lot of viral headlines conveniently leave out. And if you've clicked on other videos calling this brand new, never before seen, just happened footage, you deserve the real timeline. The Hubble image was captured on August 22nd, 2024, as part of a long-running observation program. The Webb image was captured a few months later on November 29th, 2024, using a special allocation of observing time. NASA then processed, compared, and formally released both images together on March 25th, 2026, packaging them as a joint Webb-Hubble comparison study. So no, this isn't footage from 2 minutes ago, but here's why that doesn't make it any less exciting. Science doesn't move at the speed of a viral video. Processing raw telescope data into a scientifically calibrated, publication-ready image takes real time, real analysis, and real peer review. What we're looking at is the finished product of a careful multi-year effort to combine two different data sets into a single, coherent scientific release. And honestly, that's a far more impressive story than the telescope just snapped a quick photo. This is patient, deliberate science, the kind that actually holds up. Let's actually look at what's in these two pictures, because the differences are stunning once you know what you're looking at. In Webb's infrared image, Saturn's cloud bands appear as darker orange near the poles, gradually lightening into tan tones as you move toward the equator. It's a warm, almost autumnal color palette. The poles themselves glow with a strange greenish-gray light, something we'll come back to in a moment because it's one of the most intriguing mysteries in the whole release. And the rings are almost blinding in Webb's view, appearing in an icy, neon-white glow that practically jumps off the screen. In Hubble's visible light image, taken just a few months earlier, Saturn tells a gentler story. The bands appear as pale yellow with a soft light blue hue creeping in near the poles. The rings are still bright white, but noticeably less intense than in Webb's infrared view. It's the "Hey Saturn" most of us grew up seeing in textbooks and planetarium shows, the pastel, creamy giant with the glowing halo. Side by side, these two images almost look like two different planets pulled from two different corners of the solar system. And that's the whole point. Neither image is more correct than the other. They're both true. They're just true in different ways, capturing different physical processes happening in Saturn's atmosphere simultaneously. Now let's talk about specific features, because this is where things get genuinely wild. In the Webb image, scientists identified something called a ribbon wave, a long-lived jet stream that meanders across Saturn's northern mid-latitudes like a winding river seen from an airplane window. This isn't a brand new discovery. It was first noticed decades ago, but Webb's infrared vision let researchers see it with a level of clarity that's rarely been achieved. The ribbon wave is influenced by atmospheric waves that are otherwise completely undetectable, hidden disturbances rippling through Saturn's gas envelope the way sound waves ripple invisibly through air. Just below that ribbon wave, tucked into the image, sits a small spot that represents something almost poetic, a lingering remnant of a storm from over a decade earlier. Back between 2010 and 2012, Saturn experienced what scientists nicknamed the Great Springtime Storm, a colossal eruption of turbulence that wrapped almost entirely around the planet, visible even from Earth-based telescopes at the time. That storm eventually faded, as storms do, but its aftereffects didn't disappear completely. Years later, Webb caught a lingering trace of it, a ghost of a storm still echoing through Saturn's atmosphere more than a decade after it technically ended. Think about that for a second. On Earth, a major storm system dissipates in days, maybe weeks if it's especially powerful. On Saturn, the atmospheric memory of a massive storm can persist for over 10 years. That difference alone tells you how fundamentally different the physics of a gas giant's atmosphere is compared to our own rocky little world. And it doesn't stop there. Webb's image also caught several additional storms scattered across Saturn's southern hemisphere, smaller disturbances dotting the cloud bands like scattered punctuation marks. Every single one of those features is being shaped by powerful winds and waves churning beneath the visible cloud deck, winds that can reach speeds far beyond anything ever recorded on Earth. Saturn, in other words, isn't the calm, serene, ringed ornament it appears to be in casual photographs. It's a violent, turbulent, dynamic world. And these images are giving scientists an unprecedented natural laboratory for studying fluid dynamics under extreme conditions, conditions that simply cannot be replicated anywhere on our own planet. If there's one single feature of Saturn that has captivated planetary scientists more than almost anything else in the solar system, it's the hexagon. Back in 1981, NASA's Voyager spacecraft flew past Saturn and captured something that, at first glance, seemed almost too strange to be real. A massive, six-sided jet stream sitting directly on Saturn's north pole, a geometric hexagon roughly wide enough to fit multiple Earths inside it, spinning steadily, holding its six-sided shape with an almost eerie precision. It looked LIS's like a weather pattern and more like something engineered. For decades, scientists have puzzled over exactly why this jet stream locks itself into a hexagonal shape, rather than the more familiar circular or swirling patterns we're used to seeing in storm systems here on Earth. Laboratory experiments using rotating fluids have managed to reproduce hexagon-like patterns under very specific conditions, offering some clues, But the full physics of how and why it forms and persists on Saturn for over 4 decades now is still not completely settled science. And here's what makes this particular release so significant. In both the Webb and Hubble images from this campaign, several of the pointed edges of that famous hexagon are faintly but distinctly visible, still there, still holding its shape more than 40 years after Voyager first spotted it. Its persistence across such an enormous stretch of time is itself remarkable, highlighting just how stable certain large-scale atmospheric processes can be on a giant planet, even as smaller storms. So brutally cold, hundreds of degrees below zero. Scientists studying Titan with Webb have even described weather forecasts for the moon in strikingly familiar terms, complete with methane clouds and occasional methane showers, a bizarre alien echo of Earth's own water cycle, just built from entirely different chemistry. Then there's Enceladus, a small icy moon that hides something extraordinary beneath its frozen crust, a global subsurface ocean of liquid water, one that actively vents geysers of water vapor and ice particles out into space through cracks near its south pole. Those geysers were dramatically documented by NASA's Cassini spacecraft during its 13 years orbiting the Saturn system. And Enceladus remains one of the most promising places in the entire solar system to search for potential conditions suitable for microbial life, right alongside places like Europa, around Jupiter. Seeing these worlds captured almost incidentally as background details in a broader atmospheric study of Saturn itself is a small but powerful reminder of just how much is packed into this one corner of the solar system. Saturn isn't just a planet with rings, it's practically its own miniature solar system, complete with dozens of moons, at least one with active water geysers, and another that might be the closest thing to an alien Earth we've ever found, methane rain and all. It's worth pausing here to acknowledge that neither Webb nor Hubble is working alone in some kind of scientific vacuum. This entire release builds directly on top of decades of prior Saturn research, and understanding that lineage makes the achievement even more meaningful. For 13 years, from 1997 until 2017, NASA's Cassini spacecraft orbited Saturn directly, flying through its ring system, skimming past its moons, and beaming back an absolutely staggering volume of close-up data. Cassini is the mission that gave us our first detailed maps of the rings, our first close look at Enceladus's geysers, our first landing on Titan's surface through its European-built Huygens probe, and years of direct measurements of Saturn's magnetic field and atmosphere. When Cassini's fuel finally ran low in 2017, mission scientists made the deliberate decision to plunge the spacecraft directly into Saturn's atmosphere, a controlled grand finale designed specifically to protect potentially habitable moons like Enceladus and Titan from any risk of contamination by a derelict, uncontrolled spacecraft. Cassini burned up in Saturn's clouds, a planned death that turned even its ending into one final science experiment. Since Cassini's departure, Hubble has continued Saturn observations from a distance as part of a long-running, more than a decade-long monitoring campaign known as OPAL, short for Outer Planet Atmosphere's Legacy. Every year, Hubble turns its attention towards Saturn and the other giant planets, Jupiter, Uranus, and Neptune, capturing fresh images specifically designed to track how storms evolve, how cloud bands shift, and how each planet's atmosphere changes across the seasons. It's slow, patient, methodical science, the kind that doesn't generate headlines every single year, but that quietly builds an irreplaceable long-term record. Webb, now firmly established in its own science operations since becoming fully operational in 2022, is adding an entirely new dimension to that record. Its powerful infrared capabilities extending exactly what researchers can measure about Saturn's atmospheric structure and internal dynamics. Together, Cassini's up-close legacy, Hubble's steady annual monitoring, and Webb's new infrared perspective form a genuinely continuous, multi-decade chain of observation, each mission picking up threads the others couldn't quite reach. There's one more layer of context, that makes this release scientifically important, and it has to do with orbital geometry and the passage of time. Saturn's orbit around the Sun, combined with Earth's own position in its much shorter yearly orbit, constantly changes the angle at which we view both the planet and its rings from Earth. Sometimes we see the rings nearly edge on, appearing almost to vanish into a thin line. Other times, like during this particular observation window, we get a much more generous open view of the rings tilted toward us. The Hubble and Webb images used in this release were taken roughly 14 weeks apart from each other in August and November of 2024, and that timing places them right at a specific moment in Saturn's enormous 29.5-year orbital cycle, specifically as the planet was transitioning out of its northern summer season and moving toward its 2025 equinox, the moment when sunlight falls equally on both hemispheres. Looking ahead, as Saturn continues its slow orbital march, it will gradually shift into southern spring and eventually southern summer sometime in the 2030s. Each of those seasonal transitions gives Hubble and Webb progressively better viewing angles on the planet's southern hemisphere, angles that have been comparatively difficult to study in detail up until now. In other words, this release isn't a one-off event, it's a checkpoint along a decades-long observing campaign, one more data point in an ongoing story that scientists expect to keep unfolding, image by image, year by year, well into the future. Let's take a short detour here, because there's a question a lot of viewers ask whenever they see one of these glowing, colorful space images. Is this what Saturn would actually look like if you flew past it in a spaceship and stared out too? Key window? And the honest answer is not exactly, and understanding why actually makes these images more impressive, not less. Neither Webb nor Hubble captures a single full-color photograph the way a phone camera does. Instead, each telescope takes multiple separate exposures, each one through a different filter that only lets through a very narrow slice of light, certain infrared. Wavelengths for Webb, certain visible and ultraviolet wavelengths for Hubble. In this particular Saturn release, Webb's image was built from 4 different filters, and Hubble's from 3. None of those raw filters actually correspond to red, green, or blue the way your eyes perceive color, so image. Processing specialists working at the Space Telescope Science Institute in Baltimore take each of those individual black and white filtered exposures and deliberately assign them a color, typically mapping the longest wavelengths to red, the shortest to blue, and everything in between to green, then layering them together into a single composite. This is often called representative color, or sometimes informally false color, but that term is a little misleading because it isn't arbitrary or invented. It's a careful, scientifically grounded translation, converting light our eyes could never see on their own into a color palette we can actually perceive and interpret, while preserving the real physical relationships between different wavelengths. That's exactly why Webb's image of Saturn looks warmer, with orange bands and a neon white ring system, and Hubble's looks cooler, with pale yellow bands and a softer white ring. Those color differences aren't artistic choices, they're direct, faithful translations of genuinely different physical phenomena, deep atmospheric chemistry and cloud structure in Webb's case, reflected sunlight in Hubble's. When you understand that process, these images stop looking like space art and star T looking like exactly what they are. Precision scientific instruments turning invisible data into images human eyes and minds can actually make sense of. It's also worth mentioning who's behind that meticulous work. Names like Joseph de Pasquale at the Space Telescope Science Institute, along with planetary scientists such as Amy Simon at NASA's Goddard Space Flight Center and Michael Wong at UC Berkeley, are directly credited on this release, a reminder that behind every one of these breathtaking images sits a team of real scientists and image processors, carefully translating raw telescope data into something the rest of us can actually appreciate. Now, before we wrap up, let's take a moment to be honest about something. Because it matters, especially in an era where space content online can sometimes drift toward exaggeration. Was this a real, significant, scientifically meaningful release from NASA? Absolutely, yes. Multiple official NASA and European Space Agency channels confirmed and published these images and their accompanying scientific analysis. This is not fabricated, it's not exaggerated beyond recognition, and it's not some AI-generated fantasy dressed up as a discovery. But it's also fair to be precise about what this actually is. It's not a single dramatic reveal of some previously hidden secret about Saturn. It's a carefully assembled scientific comparison, combining 2 telescopes' worth of data captured months apart, released together specifically because viewing them side by side teaches us more than either image could on its own. The genuine wow factor here isn't a shocking twist. It's the sheer depth of understanding that comes from patient, layered, long-term observation, exactly the kind of science that rarely makes for a punchy one-line headline, but that consistently produces our deepest and most reliable insights into how our solar system actually works. That distinction matters, because the real story of modern space science isn't about sudden bombshells. It's about persistence. It's about pointing increasingly sophisticated instruments at the same targets, again and again, over years and decades, until patterns emerge that no single snapshot could ever reveal. The hexagon that's held its shape for over 40 years, a storm's ghost still lingering more than a decade after the storm itself ended. A polar glow that might be aerosols, or might be auroras, or might turn out to be some combination of both once researchers dig deeper. These are the kinds of mysteries that reward patience, not hype. So where does this leave us? What happens after this particular release? For one, Hubble's Opal program will keep going, continuing its annual check-ins on Saturn and the other giant planets, adding fresh data every single year to an already more than decade-long record. Webb, meanwhile, is expected to continue allocating and observing time toward solar systems. Allows, particularly as researchers push to capture more detail on that southern hemisphere as it swings progressively into view over the coming years. There's also an entire community of researchers now working to better understand that mysterious polar glow, running further observations and modeling to determine exactly how much of it comes from high-altitude aerosols versus genuine auroral activity, a question that will likely take several more years of dedicated study to fully resolve. And on the horizon, quite literally, sits that slow, inevitable seasonal shift already in motion. Saturn's north pole edging toward its 15-year winter night, meaning the window for capturing this level of detail on the northern hexagon in full sunlight is closing, perhaps for good until the 2040s. Anyone genuinely fascinated by Saturn's atmosphere has a rare closing opportunity right now to witness one of the best documented views of that iconic northern feature that we may get for an entire generation. One last thing worth appreciating is that this Saturn release doesn't exist in isolation. It's part of a much broader project, one where Webb and Hubble are systematically working their way through all 4 of the solar system's giant planets, building a comparative atmospheric portrait of the entire outer solar system. Jupiter, the largest planet by far, has already had its storms and auroras studied extensively by both telescopes, including Webb's detailed look at the mysterious structures inside Jupiter's own polar light shows. Uranus, tilted almost completely on its side compared to every other planet, had its faint auroras first glimpsed by Hubble back